Hi scholars, welcome to Module 7. Our main topic is visual analysis. The four objectives in this video lecture are to introduce procedural reliability, describe standards for visual analysis, introduce masked visual analysis, and calculate effects using percentage of non-overlapping data and tau u. Procedural reliability is also referred to as treatment integrity or procedural fidelity. Billingsley, White, and Munson, 1980, introduced the importance of measuring procedural fidelity in intervention research. The formula generally used for calculating procedural reliability in single-subject research is number of observed behaviors divided by number of planned behaviors multiplied by 100. Be sure to cite Billingsley, White, and Munson, 1980, when you use this method of reporting mean procedural reliability. Single-subject researchers use visual analysis to evaluate individual and collective cases within studies. This way of evaluating research on interventions is nested within broader standards that we have explored in this course. For example, Cradwell and colleagues' What Works Clearinghouse Pilot Standards, or NTACT's evaluation checklist. As we critique published studies that employ single-subject experimental designs, our first task is to identify what the design is, so that we can determine whether the design allows for documentation of experimental control. Our next decision point requires that we look at the graphic displays of data to evaluate whether the data document experiment control. Documenting experimental control means that there are 3 demonstrations of an effect at 3 different points in time. That is, a predicted change in the dependent variable occurs when there's active manipulation of the independent variable. Our final step is to evaluate whether the effect matters. We might estimate effect size by calculating the percentage of non-overlapping data, or tau u. We also should critique the social validity assessment data reported on in the study. To follow the steps of visual analysis, what we will do is assess within phase patterns using level, trend, variability, and between phase basic effects by determining overlap, immediacy of effect, and consistency across similar phases. The core discriminations to make are, is the baseline adequate? Are there sufficient data within a phase to document a pattern? Is there a basic effect between 2 phases? Is there a functional relation documented by the full data set within the study? How strong is the functional relation? Luke's data are displayed where the y-axis reflects the frequency rating of the number of hits per day with a scale that ranges from 0 to 30. The x-axis reflects the number of days from 0 to 40. This AB withdrawal or reversal design has the potential for experimental control, because we can detect 3 demonstrations of effect at 3 different points in time with this design. Let's start with our within condition analysis. In other words, is the baseline adequate? Design standards suggest that 5 is the optimum for the minimal number of data points to collect per condition. However, 3 is considered acceptable. In Luke's graph, researchers plotted 14 baseline data points, which is adequate. It is not known whether hits refers to Luke physically hitting himself or someone else, or perhaps something else altogether, like number of hits or views on a personal webpage. What we can assume here is that the dependent variable, number of hits per day, was something that wouldn't have been unethical to prolong. For example, if Luke had a shunt and was engaging in the self-injurious behavior of headbanging, it would be unethical to strive for 5 data points in baseline. So are there sufficient data to document a pattern? Well, we've determined that the condition length for phase A1 baseline is acceptable, so let's now evaluate level and trend. Level refers to the magnitude of the data as indicated by the ordinate scale value. Through visual analysis, we look at the range in data point values. In Luke's graphed data, you can spot an outlying data point at session 10 where 26 hits per day were recorded. This increases the range. When the range is small, it's fairly easy to see low variability or high stability. But in the case of Luke's data, we can't immediately make this determination. Are his baseline data stable? Well, to figure this out, we first make a simple calculation of the median. The rule is that when 80% of the values in a condition fall within 25% range of the median level of all data point values of a condition, we can consider the data stable. To find the median, sequence the data points from low to high. If there are an odd number of values, the median is the middle data point value. If there are an even number of values, the median is the average of the two middle values. Draw a median line parallel to the abscissa at that value. Next, place a stability envelope over the median line at the value of 25% above and 25% below the median. Using the 80% 25% criteria, if 80% of the data points fall on or within the stability envelope, the data are stable. For Luke's data, 3 data points fall within the stability envelope, 10 fall above or below. This means only 30% of the data fall within the stability envelope. Data are not stable, they are variable. Now we can use another technique to evaluate trend. The technique is called the split middle method. We take the data within a condition and separate the first half from the second half. Then, find the mid-rate and mid-date intersection for each half. Draw a line through which the data passes through both of the intersections. To find the split middle line of progress, move the line so that there are an equal number of points on either side. Any point that falls on the line is counted for both sides. Using this method, we see most data fall above the split middle line of progress. We can say that Luke's baseline data are accelerating. The goal of this intervention presumably is to decrease the rate of hitting behavior. In phase A1, data are accelerating in a non-therapeutic direction. So far, we've used visual analysis to determine that Luke's baseline data show variability and an accelerating trend. Now we can conduct between phase analyses by examining data between A1 and B1. Let's start by analyzing the absolute level change between two adjacent conditions. We compare the final ordinal data point from the first condition, approximately 14 in A1, with the first ordinal data point in the adjacent condition, approximately 8 in B1. We can subtract to report 6 as the absolute level change. Note that the data are shifting to a lower level relative to the baseline. The trend in phase B1, calculated using the split middle method, is decelerating, moving in the direction of improvement. One way to gauge whether there is a basic effect is by calculating the percentage of non-overlapping data, or PND. To do this, determine the range of the data points in the first condition, count the number of data points in the second condition that fall outside the range of the values of the first condition, divide the number of data points that fall outside of the range of the first condition, i.e. 7, by the total number of data points in the second condition, i.e. 10, and multiply this number by 100. We get a PND of 70. This falls within the range of 50 to 70, which is considered questionable or minimal effectiveness. Is there a functional relation documented by the full data set within the study? Well, we need 3 demonstrations of an effect at 3 different points in time. We've established a minimal effect between A1 and B1. As we visually inspect phases B1 and A2, we can see an overlap or delayed effect. The data eventually accelerate in the direction of improvement, but the PND of 50 is again minimally effective. Our comparisons then between A2 and B2 show an abrupt level change, stability at a low level, but there's a low PND because all of the data points in phase B2 overlap with the data points in A2. Overall, there is not a strong functional relation in this display. On the next slide, I will display a graph from a published study. The top graph is Veronica's total duration of cell phone usage in minutes per data session. The bottom graph is the percentage of all students using cell phones in the class. The goal in this intervention is to reduce cell phone usage, so we're expecting to see treatment data decelerate. Question 1, is the baseline adequate for the top graph for Veronica? There are more than 5 data points. The researchers end data collection on an outlier at a high value. We might not be able to accurately predict where that next data point would fall, but we can tell that data are not moving in a therapeutic direction. Are there sufficient data within a phase to document a pattern? Yeah, there are sufficient data within the phase to document the pattern. Is there a basic effect between the two phases? We see a level shift between baseline and treatment. In treatment, there is low overlap, and we see a decelerating trend and stability at a low level. We could call that a basic effect. So the question for you is there a functional relation documented by the full data set within the study? For those of you who want to work on improving your visual analysis skills, software is available online at the website www.singlecase.org. I have linked this website on our course site. Masked visual analysis. Traditionally, single case experiments follow a response-guided approach where design decisions during the study are based on participants' observed patterns of behavior. However, this approach has been criticized for its high rate of type 1 error. In masked visual analysis, response-guided decisions are made by a researcher who is blind to participants' identities and treatment assignments. Masked visual analysis also makes it possible to conduct a hypothesis test assessing the significance of treatment effects. The first step in using masked visual analysis is to set the study parameters. The research team should agree upon the design, minimum number of data collection points per phase, whether or not to use randomization, for example, randomizing the order of participants, randomizing the intervention start point. Step 2 is to split into 2 teams. Decide on members of the analysis team who will visually analyze data and direct the intervention team, and then members of the intervention team who will conduct the study based on the agreed upon parameters and the direction of the analysis team. Step 3 is to conduct the study. The intervention team begins the study and sends the collected outcome data to the analysis team. The analysis team analyzes the data and makes decisions about when it would be appropriate to make a random assignment. The intervention team makes random assignments when directed by the analysis team and continues to collect and send outcome measures to the analysis team, but they never disclose the results of the random assignments. Finally, the analysis team indicates when the study should be concluded. Step 4 is to compute the p-value. The analysis team specifies what they believe are the results of the random assignments. If the intervention team indicates that they are correct, then you can report the p-value. If they are not correct, the analysis team continues to make specifications until a correct specification is made. Here, the p-value is computed as the number of specifications divided by the number of possible assignments. So let's run through this with an example. In our example study, the research team is going to conduct a multiple baseline with 4 participants. the study relates to percentage of time on task. The team agrees that they'll collect at least 5 baseline observations. They'll have 2 observations in the stagger, meaning that they'll stagger the intervention across participants. So some will remain in baseline, others will move to intervention. That stagger time has to be a minimum of 2 observations. And that the treatment phase will last at least 3 observations. The team agrees to randomize the order of participants for the intervention. We've got 4 participants, so they're going to randomize who goes first, second, third, and fourth. This gives a P of 4 factorial, or 24 possible assignments. If the treatment has no effect, the probability that a masked visual analyst could identify that correct order would be 0.0417. To contrast what we've established so far in this example with how traditional multiple baseline design studies using a response-guided approach run. The example on this slide is a study that I conducted with my colleague George Peterson Carlin and Tara Kazarowski. In this study, we evaluated the effects of the power strategy for writing instruction, and we evaluated intervention effects for students using pencil paper methods of composing. Concurrently, we evaluated those effects for use of voice typing with word prediction assistive technology. So in the graphic display here, the baseline data for Max, it appears there's 2 data points. There are 4 because of the concurrent design, are moving in a direction that goes against what we're hoping, right? We want to see an increase in number of correct writing sequences on his explanatory responses, but here data are fairly stable but decreasing. We don't collect data during the intervention because we weren't necessarily interested in recording what the participants were picking up as we were using this explicit instruction of modeling practice. However, once they'd met our criterion, we wanted to see independent performance level. So we're comparing the baseline to the performance level after they've learned the strategy. We decided to start with Max and then introduce the intervention to Emily after we had Max meet criterion and Emily's data were stable. It made sense to intervene with her. We kind of used this just eyeballing stability in the participants and matters of convenience. For whom did we most need to intervene soon? Our final participant here was performing at a relatively high level, and so prolonging baseline wasn't really detrimental for this particular student. So we didn't use any randomization in this process. We used the typical response-guided data collection procedures for a multiple baseline. In our example, we're going to see what happens when we split into 2 teams and we conduct this study. So here we're running through this as though we are members of the analysis team. Our team has randomized the order of participants. They did not randomize the intervention start point. This means that our task as analysts is to determine which tier, meaning Wendy, Rob, Tom, or Joel, was exposed to the intervention first, second, third, fourth. So here's what our data collection team members are sending us. And we're looking at this as they're conducting the study, trying to determine the order of participants based on just our visual inspection of this data. So let's make some specifications. Let's say that we think they intervene first with Joel. Right, we see a level shift right here after this break. And then maybe the next participant was Wendy. We see a level shift after this break here. The next participant we could say would be Rob. After the break here, we see a level shift. And then Tom would have been the final participant. So we would specify Joel, Wendy, Rob, and Tom. Now, if we're correct, the effect is determined to be significant. The probability that a masked visual analyst could have identified the correct order of intervention implementation if no differences existed between baseline and intervention is only 0.0417. So that's how masked visual analysis works and can help account for some of the issues with accuracy that we face in the critique of type 1 error. Calculating effects. We practiced using percentage of non-overlapping data. Another approach for analyzing single case experimental design data combines non-overlap between phases with intervention phase trend and can correct for baseline trend. It's reported on this -1 to +1 scale. So we conduct pairwise comparisons across phases. This results in a positive, negative, or tie for each pair. And then we use the formula to calculate a tau u score. For those of you not wanting to do a calculation by hand, I've linked on Canvas the tau u calculator and also a video demonstrating how to input and run your calculations on this tau u calculator.